everybody. So I'm Rebecca. I have been enrolled in Math Study Skills this quarter, and for the final presentation, I have chosen to do the Pythagorean Theorem. This should be a refresher for most of us, as I feel like this is definitely taught um, early on, especially in high school. But the good thing about this is we can definitely see it day to day, and the application does not just stop in school, but also in real world. So I hope from my presentation you can definitely learn a little bit more. Okay, so to get started, we're just going to be talking about the basics. What even is this theorem? So this is one of the most studied and has the most proofs in geometry. Definitely something that once you have a basic understanding of this in geometry, it gets more complex once you start adding trigonometry into it, calculus, and also algebra. So it's just any right angled triangle. The two shorter sides are going to be a squared and b squared. These are called the legs. And then most of the time we are solving for c, which is the missing length. But not all the times. We could have side b and c and not a, or vice versa. We could have a and c and not b. So by this theory, we can find the missing side of a triangle. An example here that I've included is this image just to visualize it for you, and also with this equation. So we're going to have the legs as 3 and 4, squaring them each equals c squared. Doing that conversion gets us to 9 and 16, square rooting those together, and then c will get us to 5. So there we go, we found the missing length. So this theory was originated, honestly, people don't really know who was the first to come up with it, but we do know who it was named after. It was a Greek mathematician. He had a school of thought down in southern Italy, and this would be things between arts, music, philosophy, and also mathematics. Some evidence is going to show us that even before Pythagoras knew about this and founded it with his name, named it. People don't know if it's the Chinese, Babylonians, Indians. It was kind of all independently discovered over the world. Um, and we definitely do have some artifacts of this. We have writings of it in clay tablets from the schools with Pythagorean triples, which I'll talk about later. It's just whole numbers that satisfy this formula. And it just shows how we can use it in surveying class, but also in construction and like with Indian text altars. People use it in schools, churches, because we have very profound architecture all over the world, especially with the pyramids in Egypt. And there was definitely early proofs of this, visual and geometric. You can rearrange squares on the triangles, which you can actually see in this image. So I'm really glad that this image included it. Okay. Okay, so I wanted to add a little bit of fun, so I'm going to have some facts for you guys. Like I said, it's one of the most proven theorems in math. Hundreds of proofs, even ones by our president, James Garfield. The Pythagorean triples are numbers like 3, 4, 5, 5, 12, 13. There's an entire list of them. This just helps us easily identify, and these have been used for thousands of years. It can be shown because you can rearrange triangles on a right triangle side, or rearranging squares on a right triangle side. So it's definitely an aesthetic and visually satisfying theorem, which is not very common for a lot of them. Like I said, it was kind of independently discovered, um, and you can use this today with GPS navigation, just kind of calculating distances between 2 points. Instead of taking 2 separate legs, you can just kind of take a shortcut and use that C angle, or C side. Okay, here's another fun fact. So this is also used with archaeologists. They can use the Pythagorean theorem whenever they're doing field excavations. They're going to start a dig and they place a grid over the site surfaces. They're going to lay out something very accurate, and they can use the theorem x squared plus y squared equals z squared. Once they get the baseline sides, like the x and y, aka the legs, the proper length of the diagonal is calculated by using the theorem to make sure the quadrants are rectangle and not a lopsided shape. Corner stakes are placed to mark so that they have the accurate location of the site and they know where to begin digging. And then overlaying rectangular grids uses the mathematical idea. I tried to pronounce this and it's definitely a tongue twister. Cartesian coordinate system. Okay, so here's my example here of the real world. So we're going to have a pilot, because my dad's a pilot. So he definitely tells me all the physics and the calculations he has to do on a daily basis just with air, wind. Obviously, their main priority is getting everybody there promptly and safely. So I thought this was pretty applicable. So this pilot flies from point A to B. The first leg is going to be 120 miles north and 160 miles east to reach the final destination of Chicago. Instead of flying two legs, he wants to calculate the direct path, and he can use this theorem. So we're going to have c squared equals 120 north, and then we're also going to have 160 east, which gets us to the square root of 14,000 plus 25,600, which gets us to the square root of 40,000 is 200 miles, which is shorter and more efficient. This can be easy because clear right angles northeast and east-west. The math is straightforward, which is going to save time and fuel, but sometimes this can be complicated because math isn't that simple, and whenever we're using right angles, we have a curved spherical Earth. So we're also going to have wind restrictions. There might be restrictions with air traffic control saying you can't fly this way because you're going to crash into another plane. Maybe with air pressure, you're going to have to go a little bit lower. So lots of things to take into consideration. It's not just as simple as taking a little detour. Okay, now I found this really interesting, is you think that it's just for triangles, but we can use it to calculate the diagonal of rectangles. So here we can find, it's just basically putting two right triangles together. This one also, so not just with rectangles, we can also use a square. Since, like I said, it's a very satisfying theory, so instead of putting squares on the outside of all the sides of the triangle, we can kind of reverse it, and we can put triangles on the outside of the squares, or on the outside sides of the square. And then we can easily identify our legs, and then obviously all the inner corners of the square will be labeled C. So then we can find out how big a square is based on triangles in this theory. And then the last one is just another application. This one's just a little bit of parallelogram, once again putting three different triangles together to make a larger shape. Okay, so I use the example of archaeologist and also a pilot, but this instance is going to be with GPS. We can use it to make straight line distances. Even in sports, if we know a player's strengths and weaknesses and we want to put our best player on the field, but they can't shoot this far, they can't shoot this high, they can't shoot this long, we can navigate that, or calculate that, I mean. Let's say he's running 15 feet along the baseline, 20 feet up the court, and then he's going to go diagonal towards the hoop, which is 25 feet. Drone paths, similar to the aviation, like I said. Computer graphics and video games, calculating the distance between 2 points. If we kind of want to be incognito mode based on our opponents, once again, kind of taking the quickest path. And then the most obvious application is definitely with construction workers and architects. Since triangles are the strongest shape in all of architecture because the weight is evenly distributed, this theorem definitely comes into practice here. And then this one was kind of more personal, just like if you have a ladder at your house and you're trying to install Christmas lights, how high can the ladder reach is going to depend on how far away you have it from your house, and then obviously the height of the ladder itself. So this example is 10 feet long, 6 feet from the wall. How high is it going to reach? That would be our C. That's what we're trying to find. Okay. So obviously no theorem is going to come without its weaknesses. So like I said, this example in the top right corner, the Pythagorean theorem is definitely something you want to kind of have a good baseline understanding of before you can advance to more complicated topics within algebra, trigonometry, and even calculus. That looks very over my head, I will just say. Whenever you're dealing with sides that are going to be decimals, you might even have square roots on the sides if it's really complicated. So that might take away from the aestheticness of it just because you're going to be messy dealing with not whole numbers or even irrational numbers. Obviously, you're going to have to be able to differentiate between a right triangle and a different type of triangle. Real world distances aren't always measured at perfect right angles. Like I said with the pilot example, our world is round. Then if students aren't able to know the real world applications of this, they're going to think it's kind of abstract and they're not going to understand the point, and they might not be as more engaged and confident about learning the material. And then next we have just the websites. I definitely want to do some background research on this, and get a little feel just on basic information. I wanted to dive a little bit deeper, so here's my resources, and I really hope you guys enjoy this presentation. I really enjoyed learning about it, and I hope I was able to give you something else to just remember whenever you are applying this theorem, whenever you encounter it in your homework, and I really am hoping you took something away from this. Thanks.